Hello everyone and welcome to the fifth video of the LTSpice part of this course. Today we will be looking at how to build and analyze simple three-phase systems using the LTSpice software. Three-phase is commonly used in electricity and especially in energy because it has many advantages. A first advantage, which we have seen in class, is the fact that it requires only 3 wires. One per phase when the load is balanced and a fourth when the load is not balanced. A wire is then required for the neutral. Moreover, three-phase is natural when there are rotating systems that operate by induction, such as generators or asynchronous motors. Let's take this generator as an example. It is a magnet that rotates on itself, creating in turn induction of voltages in each of the coils it passes by. The magnet, as it rotates at a constant speed, passes successively past each of the coils and creates voltages that are 120 degrees out of phase, i.e. the angle between the coils. It is therefore natural that we have three-phase voltages in these three conducting wires. If we represent the three-phase current as a complex phasor, we can easily see the 120 degrees phase shift between the voltages. If we let the phasors evolve over time, we can see by taking their sign that the voltages that are created are actually 120 degrees out of phase with each other, with a peak amplitude equal to the norm of the complex phasor. Here is a three-phase star circuit made using LTSpice. Although the graphical constraints imposed by LTSpice prevent us from immediately seeing that it is a star circuit, it is nevertheless easy to convince ourselves of this. The output potential of each load is the same and is equal to the potential of the neutral wire. At the input, we have for each load the potential of the corresponding phase. The loads are balanced. For each phase, we have a load which consists of a 200 ohms resistor in series with an inductance of 2 henries. This value of 2 henries may seem a lot to you compared, for example, to your electronic course where you worked with milli, micro or even nano henry inductors, but this is linked to the fact that in energy we use very low frequencies. Here 50 Hz, which is the frequency of the electrical network in Europe, which would be 60 Hz in the United States. The low frequencies mean that if we want to have a significant impedance corresponding to this inductance, we need a very high inductance value. In fact, the value of the impedance related to an inductance is proportional to the frequency. We have chosen as voltage 325 volts peak, which corresponds to 230 volts RMS. We divide by square root of 2, formula seen in class. This corresponds to the voltage of the phases in the domestic network in Europe. Your 230 volt socket at home is nothing more than one of the phases of a three-phase system. In common parlance, we say 220 volts, but the network has been updated at 230 volts for a few years now. It is a transition that has been made gradually, but which allows energy to be saved in heat losses. In fact, higher voltage means lower current and therefore less Joule effect and therefore less heat loss. For the anecdote, if you try to plug a device made, for example, 40 years ago, which was therefore designed for 220 volts, it might burn out because of this 10 or even 15 extra volts. Concerning the characteristics of this circuit, we can also see that the voltage sources have been shifted 120 degrees out of phase with each other, one at 0, one at 120, and one at 240 degrees out of phase, which allows us to have a three-phase circuit. If we analyze the circuit, we will have three-phase voltages as we expect. Furthermore, we can see that what we have seen in class concerning the current in the neutral wire is correct. In fact, if we sum the currents in L1, L2 and L3, it is the currents in each phase. The formula is Y of L1 plus Y of L2 plus Y of L3. We have a constant current of 0 ampere. So no current, we could very well remove this wire. In fact, we will do so later. We can see the transitory regime, which I have deliberately left visible. It is the moment when the circuit starts up and things happen that we don't necessarily have the means to calculate, and that LTSpice calculates for us. We are very happy about this. It is interesting to note that even during the transitional regime, the sum of the currents is equal to 0 ampere. We have demonstrated this theoretically, and it's really true all the time. If I remove this neutral wire, we can redo the analysis and it happens exactly the same thing. Now, let's try to put the neutral wire back on so that we can unbalance the load. Here, I put 3 Henries instead of 2 Henries, and here 100 ohms instead of 200. If I do the same analysis with the 3-phase currents and then their sum, I realize that the sum here in turquoise is neither constant nor 0. So, an unbalanced system needs a fourth wire. In the domestic network, there is a neighborhood transformer which takes care of keeping the loads permanently balanced so that on the main network only 3 wires are needed. We will now show some further results of the course by means of the LTSpice simulation. I will first show the rather simple but important result, which is that the voltages of each phase when summed up give us 0 volts, which is a basic principle of 3-phase. If I take these 3 voltages, which as we have seen are out of phase each time by 120 degrees, and I sum them up, I get a constant total of 0 volts, which is this turquoise line here. I can also see that the line voltage is the difference between the voltage of one phase and the voltage of another phase is equal to the square root of 3 times the phase voltage. It is the voltage at the terminals of this load. We are going to calculate the voltage difference and represent on the same graph as simple voltage and this compound voltage, which is equal to, I take the cursor to see exactly how much, 562 volts, whereas the simple voltage was 325 volts. So it is indeed square root of 3 times 325, which is equal to 562. We can also see that this 562 volts peak corresponds to an effective voltage of about 400 volts, which is, for example, the voltage used by a number of ovens or washing machines. In fact, ovens and washing machines are connected on 2 phases in order to have a higher effective voltage, which they can use for their great need of power. In the old 220 volt system, this compound voltage was about 380 volts, which is also found on many household appliances. It is also 2 phases, simply. the voltage of one phase was rather 220 volts and not 230 volts as it is the case here. Finally, the property that the phase current is equal to the line current in the start circuit is immediately verified because Kirchhoff's law tells us that the current which is supplied by this source necessarily passes through this impedance because there are no nodes in its path. I can check this with LTSpice. Always pay attention to the direction of the currents in LTSpice. There it is measured in one direction, there in the other. Then I could turn my resistance to measure it in the right direction. I am not going to do that, but you have to know that we will have a 180 phase shift. That's what we have here. This property is immediate for the start circuit. Here we have a three-phase delta system. Again, it's not necessarily obvious at first glance, but you can see it by naming the nodes with clever names. The input of the first load is the same node as the output of the third load. The input of the second is the same node as the output of the first. The input of the third is the same node as the output of the second. This is the definition of a three-phase delta system. As far as the sources are concerned, we keep the same. It is the same three-phase 230 volts effective at a frequency of 50 Hz. The phase shifts are respectively 0, 120 and 240 degrees. The load is the same as before with a 200 ohms resistor in series with an inductance of 2 Henries. We can see from this excerpt from the course that this circuit and this circuit are completely equivalent. So, this is the right-hand variant that we have reproduced with LTSpice. We can easily check the property indicating that the line voltages are equal to the phase voltages even without LTSpice. Indeed, to measure line voltage, i.e. the difference between two phases, I have to take the voltage at this node here minus the voltage at that node there. i.e. this one minus that one. You can see that at the impedance terminals it is exactly the same thing that you measure, because the impedance is placed between this node here and that node there. It is a link between the same nodes. We can see that this voltage is equal to the line voltage that we had in the triangle circuit, i.e. 562 volts, that is to say the 325 peak volts of earlier, multiplied by the square root of 3. The property here, indicating that line current is equal to the square root of 3 times the phase current in a delta system, is not as immediately verified. However, this can be measured with LTSpice. Here I have measured the current in R1 and the current flowing out of V1 divided by the square root of 3. Again, we have the same problem with the direction of the current, which creates this phase opposition, which is not very sympathetic, but we can see that we are dealing with the same current with this square root of 3 adjustment in amplitude. Something that is perhaps interesting to note is that this relation here, it has tensions in a triangle system, and this relation there, it has currents in a star system, are valid whether the load is balanced or not. On the other hand, these relationships here and there, it has the voltage in a star system and the current in a triangle system, require a balanced load to be true in general. So maybe we can quickly check this. I will unbalance my load here, for example by changing the value of the resistance and inductance, and carry out the analysis. You can see that I no longer have the same values. On the other hand, you can see right away that the relationship concerning the tension will still be true. I can't even show you with LTSpice because in any case I will put my probe at the same node to measure the line voltage and the phase voltage, so I will obviously have the same result. In other words, these relationships here are immediately derived from the most fundamental laws of circuit analysis. However, those have been demonstrated, and the demonstration no longer holds if the load is not balanced. In the last part of this video, we are going to add a few additions to what has been done so far, as well as study the power of three-phase circuits. You can see that I have made some addition to this three-phase triangle circuit that we had already taken care of earlier. The reason why I did this is that I don't want to study it only at 50 Hz, but to study it over a wider frequency range, from 1 to 10,000 Hz, in order to show the generality of what we have seen. In order to do this, of course, I have to modify the voltage source and adjust it to be able to use it with the point AC command. I use the AC amplitude of 325 volts and the phase of 0, 120 and 240 degrees respectively. In order to be able to adequately measure the voltages and in particular the current through the load, I have modified my load, which was earlier composed of an inductance of 2 Henries in series with a 200 ohms resistor, and I have integrated the series resistance directly into the definition of the inductance. Indeed, the most observant among you will have noticed that until now I was only taking the current from the resistor here. If this was quite suitable for what we wanted to demonstrate with the sine at 50 Hz, in a frequency analysis, it would be simpler to take a single current measurement directly here on the inductance, to which I have included a series resistor, so that we can have our real part and our imaginary part in a single calculation. Also, the previous approach of taking the current only on the resistor could play tricks as far as the phase is concerned. We can start by checking that one or the other law that we saw earlier in the time domain with sines is still valid in the frequency domain. Let's take this three-phase triangle circuit as an example. We know that the line current will be equal to the square root of 3 times the phase current. If I measure the line current and the phase current, I will display the value of the currents linearly and multiply the phase current by square root of 3. If all goes well, I should only see one current curve. This is the case. On the other hand, we see that these currents are not in phase. This is not surprising because we don't have a law that tells us that in general these currents are in phase 2 by 2. The last notions here are mathematically obvious if we have demonstrated the above relationships. However, we will quickly do this with LTSpice in order to be able to see that is true. I have therefore represented on this graph on one side in red the power emitted by one of the sources. As we have a balanced system, it must be a third of the power consumed by the circuit. So, if I want all the power consumed by the circuit, I have to multiply this by 3. Here, I have represented a line voltage multiplied by a line current. So, if I want this for the whole circuit, as we are in a balanced circuit, I can multiply it by 3 too. I have divided each of these results by 2 because we have been working with peak values up to now. The power we are interested in is the effective value, so I have to divide all this by 2. Finally, if I multiply the line current by the line voltage and by the square root of 3, I obtain two curves that overlap perfectly. This is the power consumed by the whole circuit. You shouldn't pay attention to the phase because it's not correct, because you have multiplied 3 times what was happening in one place and not on the whole circuit. And as we said earlier, there is no reason for the phase and line voltages to be in phase 2 by 2. So we are arriving at the end of this video. Thank you for your attention. Don't hesitate to ask questions if you have any, either on the Moodle of the course or as a comment below this video. I also encourage you to try out these 3-phase circuits at home with LTSpice. We will try to make the files used for this video available. In particular, I encourage you to test the power relationships we have seen with the triangle circuit and the star circuit. We did not do this in this video, but the way to check it is quite similar to the way we did for a triangle circuit. Thank you and see you soon for more videos on LTSpice.